This is the first in a series of weekly webinars that our energy and environmental stewardship team has put together. So we thought we would give you something that maybe not directly related to the current situation, is still something that folks will find some interest in, maybe something that you would like to know more about, maybe didn't have the opportunity to find out more about during regular time. So what we're going to do is go through these slides, and we'll leave time for questions at the end. We'll put those in the chat box, and we'll try to get through as many as we can. If people want to stay on afterwards, past the 2 o'clock time frame, I'm fine with that. But we will try to end things up for folks before 2 o'clock passes. So with that, let's go ahead and get started today. So again, what we're going to be talking about is different types of things that you might see in the atmosphere. And when you look at the atmosphere, look at the sky. You know, I'm looking outside my window right now and I see this beautiful blue sky. I see all these fluffy white clouds, but there's lots of things out there that people may see from time to time and not really know what's going on with it. For example, this picture that you're seeing right now is, it's called a fall streak. And what's actually happening in that cloud layer, it looks like there's a big hole. Well, the reason that hole is there is if you look right in the center of that picture, you see these little thin feathery type clouds. What those are ice crystals. They've fallen from a higher level down through that cloud deck. And essentially what they've done is they've robbed the water out of that lower cloud. And so that's what opened that cloud up and made that hole there. And you can see that fairly often, but things like that you may have looked at before and wondered what makes that happen. So we're going to try to talk about that today. We're going to try to talk about some things that a lot of people have probably seen before, but maybe wondered what was going on. And we're also going to talk about some things that maybe you haven't seen before and might find some interest in. So the first thing that we're going to deal with is something that is out there, and we see it every day. We see it here today, but you want to know what the reason for that is. And we're going to talk about what makes the sky blue. Out of all the energy that the sun puts out, it sends out these rays or beams of light, and as those beams of energy go out, they're going out pretty much in a straight line, but they're also going out in waves. And of all the energy that the sun puts out, we see just a really tiny fraction of all that light. And we call that the visible spectrum. Now, normally, we just see that light as white light because all those different wavelengths in that visible spectrum are mixed together. But we can separate those wavelengths out. And if we do that, we see those as colors. We'll see those shorter wavelengths that we can see are actually in the indigo or violet part of the spectrum. Our eyes don't really see that really well. So typically we talk about the blues, the greens, the yellows, the oranges, and the reds. The wavelengths on these, if you're wondering what a wavelength is and you're looking at the slide there and you see where it says one wavelength. So that's the top of one wave to the top of the other. That's just the wavelength. Now, when would we normally see these? Well, some of you may have seen them last night when we had those thunderstorms come through, and after they had passed through and the sun came out, you saw some rainbows. And that's exactly what happens is when we break those fractions of wavelengths out, we see those as colors. Now, this next slide, one really neat thing to talk about is out of all that energy that the sun puts out, all the different wavelengths of light that's there, we see just a tiny fraction of it, but what actually makes it through the atmosphere is in that visible spectrum. Amazing how that works. The wavelengths are really, really tiny. If you can see the bottom of that slide, and you may not be able to see all of that down there, but if you notice those numbers, those are in something called microns. A micron is 1,000th of a millimeter. Really, really tiny. And you can see that visible spectrum. We're talking about it ranging from 0.4 to 0.7 microns. In that visible spectrum, that's most of the energy, or the majority of energy that actually comes through the atmosphere, is what we can actually see. These wavelengths are really small. But the other thing I wanted to point out with it before we get off this slide is that you see two humps there. That first hump that's on the left with the colors, that's the energy that's coming in from the sun. Then you notice a second hump that has longer wavelengths to it. That's the energy that's going out from the Earth. And this is a really important point because especially if there's folks out there that like talking about climate change, greenhouse effect, those kind of things. And this is one of the things that I always try to tell my students in my weather classes is that whatever energy comes in from the sun, it does go out. Greenhouse gases do not trap heat. What they do is slow down how fast it's released from the Earth. So that's a really important aspect to go along with that. So again, whatever comes in from the Earth goes out. Now we can talk about microns and say they're really, really small, but to try to give you a visual, if we blew up a human hair to the size of that big circle that you see there, a pollen grain would be the size of that dark circle, and a micron would be that little dot. So these wavelengths are incredibly small, really, really tiny. Now, as these come through the atmosphere, they bounce off the air molecules that are out there, and we have mostly nitrogen and oxygen in the atmosphere. So as these wavelengths come down, especially the smallest wavelengths or the shortest wavelengths, those being in the blue category, they hit an air molecule, they bounce off and they go in another direction. Another one comes in, bounces and goes off in another direction. So all those blue wavelengths just get scattered all over the place. That is why we have the blue sky, is because that blue part of the spectrum is just getting scattered all over the sky. That's why we see the blue sky during the day. Once the sun goes down, then you can see the stars. So go out, tell your friends and neighbors. But if you do so, please do so at a safe distance. Now the longer wavelengths, especially the reds, you're typically only going to see those more directly from where the sun is, because those longer wavelengths can still make it through the atmosphere. And again, they're not getting scattered quite as much. Another thing to talk about is, and today isn't a good example as any, if you go out and especially on a day where you have very few clouds out, you look up almost directly above your head and the sky looks fairly dark blue. But the closer you look towards the ground, the lighter it seems to be. And the reason for that is because of where those water droplets are. Water and water vapor both stay pretty close to the ground. And if you've ever flown in a commercial jet, you can kind of see that. Once you get above several thousand feet, you kind of see this haze close to the ground. That's all that water, not only water droplets, but water vapor. Those help scatter all the light well, also. And so that's why you also see that whitish color when you get close to the ground. And here's an example of that. If you look at the top part of the slide, you see the darker blue. You look down towards the ground, and you see where the sky looks whiter. Now, how many of you have been to the Blue Ridge Mountains? All right, I'm imagining a few people nodding their heads or waving their arms or whatever. So I'm guessing that there's been a few of you that have made it to the Blue Ridge Mountains. And if you have, you notice that they do look blue. Well, what causes that? It's actually the trees. What the trees do is they actually give off natural hydrocarbons. And there's one of these in particular called terpenes that, as they're given off, they also react with some natural ozone that's present at ground level. Now, ozone is just 3 atoms of oxygen put together. We don't have a bunch of that at ground level, except when we have ozone alerts in cities. But that's a totally different subject. But when you've got this natural ozone, it reacts with the terpenes from the pine trees, and those particles scatter that blue light, and that's what creates those bluish colors to the mountains. Now, that not only happens in the Blue Ridge, it happens in other mountain ranges as well. This picture was taken about 6 hours ago, or maybe about 5 hours ago. Now, out of those different colors that we can see. Why is the sun yellow when it gets up? And it's actually because it's an optical trick that's being played on us. Because what that's doing is the green and the red of the sunlight is combining, and we see it as the yellow color. So we actually see greens at other times of the, or we can see greens, only our eyes are deceiving us in the color that we see. Now, other times, especially at sunrise and sunset, we have that red sun and we have the red sky. So what's happening there is we have to think about how far that sunlight has to travel through the atmosphere. The longer the distance it has to travel, the more wavelengths get scattered away. So when we're looking at a sunrise or sunset, that sunlight has to travel through a much longer distance of atmosphere to reach our eyes. And so the blues, the greens, the violets, all of those get scattered away. The only thing that's left for reaching our eyes is the reds and the yellows. And so that's why we have the red sky in the morning or the red sun in the evening. Makes for really pretty sunsets though, and really pretty sunrises. Probably not as many people see the sun rise as they do the sunset, but both of them are really, really pretty to look at. Now, other times of the year, and you may have noticed this like on a really sticky, humid summer day, where you go out and you look in the morning, the sun is still red at 9 o'clock in the morning, or you go out later in the afternoon and the sun is already red by 3 or 4 in the afternoon. That's because there's so much water vapor in the air that also scatters away all the shorter wavelengths of light. And so the only thing that can reach our eye is that reddish color of the sun. That's the only color that's left for us to see. Another thing that can do that is if you have a lot of smoke or dust or those kind of things in the air as well. Now, about 20 years ago, some folks may remember that right about this time of year, we had smoke coming in, actually from forest fires down in Mexico. We had really strong southerly winds bring that smoke up, and for about 3 days, we had just a blood red sun throughout most of the day, each of those days. And that's the reason why, because that smoke was filtering out all those other wavelengths of light except for the reds. Okay, now the next thing that we're going to talk about, and this is going to come back on several things that we're going to deal with, is when sunlight travels through different densities of air, and this can be caused by air of different temperatures, it will actually change the direction of that light, and that's called refraction. So if it travels from a more dense layer of air, like if it was really cold air, into warm air, which is less dense, that will actually change the direction of light, and vice versa. So how does that play in different things? Well, one of the things that happens is when you see that sunrise first thing in the morning, it's actually still below the horizon. When you see that sunset at night, that sun has actually already gone down because those light rays are being bent right at the horizon because it's going through denser air. And so how that plays out is we actually see that sunrise about 2 minutes before the sun is actually above the horizon. And we have a 2-minute lag on that sunset as well. We see that sun for 2 minutes after it has actually already gone down. And so we actually gain about 4 minutes of daylight simply because of that phenomenon. Another thing we can talk about, and this is something that I think everybody has seen, you go out on a day, maybe a little bit cloudier than today, where you've got a lot of these puffy cumulus type clouds that are maybe kind of forming a layer, but you got breaks in them. And that sun, you can see it streaming through those breaks in the clouds, and you see these bright rays of sun coming through there. And I can remember when I was a kid asking about this when I was probably 5 or 6 years old, and I got told something. I don't remember exactly what it was, but I believed it for years and years. But anyway, these are called crepuscular rays. And again, they just look like these shooting beams of light coming through the clouds. And they always look like they're spreading out. They're not. They're actually all parallel It's just one of those things that our eyes, again, are kind of deceiving us. It's kind of the same thing as when you look down the road and it looks like the road converges to a point. So it's just a matter of perspective. Kind of the same thing. I always hear a lot of people say that they believe that storms, when they come to their area, as they get closer, they split apart. Well, more than likely, they were already split apart, but when you look at it off in the distance, they look like they're all together. So it's just a matter of perspective. Again, really pretty to look at. You can see how those beams look like they're spreading out from this perspective. This is one from a plane. I really like this one. And then probably everybody right now would kind of like to be wherever this is. I'm not sure exactly where this is, but you can see those light rays there. Again, look, they look like they're spreading out, but here's a little different perspective. This is from space. And you can see those light rays there, and you can see they're all parallel to each other. So again, sometimes what we see is not actually what's happening. The opposite of crepuscular rays are called anti-crepuscular rays. These are going to be seen in the part of the sky opposite from where the sun is. And they all look like they converge down to one point. Again, those rays are parallel to each other, but it's just how we see it. And that is what anti-crepuscular rays look like. I don't think many people see that as often as we do as the crepuscular rays, but still really neat to see. Next thing I want to talk about is twilight. And twilight is that time right before sunrise that we start seeing more and more light in the sky. And then at nighttime, right after the sun sets, and we have light until it gets entirely dark. Twilight has actually been divided into 3 types of twilight. And this actually has been legally defined. For example, say somebody has a car accident and maybe the amount of light that was present comes into play. These different types of twilight will relate to that. Civil twilight is when the sun is anywhere from 0 to 6 degrees below the horizon. Nautical twilight is when the sun is 6 to 12 degrees below the horizon. And astronomical twilight, right before darkness, or right after darkness, if it's morning time, is when the sun is 12 to 18 degrees below the horizon. Now again, we can tell you these numbers, but what does that really look like? Well, here's an example of civil twilight. Again, you've got lots of light out there, still very easily seen for objects. Nautical twilight, it's beginning to get fairly dark, and actually it's called nautical twilight because at this time you can start to see stars in the sky. And so that's when sailors would be able to go out and use their instruments to find out where they were actually located at. Astronomical twilight, just a little bit of light left, lots of stars very visible. A couple other things to mention what's twilight. And maybe some of you have actually done this or been in these areas, like in tropical locations or near the equator, but you may hear people say that if you're in those tropical locations, when the sun goes down, it gets dark really quick. Or in the morning time, it's like it's dark and then boom, it's daylight. Well, that's because that actually is fairly close to being true, that at the equator and in those tropical areas, twilight is not nearly as long. And that all has to do with how the sun rises and sets. If you're near the equator, that sunrise and sunset is almost straight up and down, or very close to it. The farther you get away from the equator, that sunrise and sunset is at more of an angle. And so it takes longer to go through those degrees below the horizon, and so you have a longer period of twilight the farther you get away from the equator. So to give you an example, at Rio de Janeiro, their twilight averages about 2.7 hours per day. At Fairbanks, they have almost 6 hours of twilight. And then for a period during the summer, they actually have no astronomical twilight. By the time you get to the poles, and everybody always hears that the poles have 6 months of daylight, 6 months of darkness. That's not exactly true, because at the poles, that angle is such that it takes a long time for that twilight to go through its phase. And so, for example, at the North Pole, when that sun goes down, there's actually about 2 months of twilight before it gets totally dark. And then before the sun rises in March, there's about 2 months of twilight as the sky lightens up. So in total, the North Pole only has about 11 weeks of total darkness, not 6 months. Some of you may have also heard of something called the green flash. And I have never seen it myself. I've just seen pictures. But right when the sun rises or right when the sun sets, just for a brief instance, right at the top of the sun, you'll have this instant of a green flash of light. And again, probably the vast majority of us have never seen that. So let's see what the green flash looks like. And there's the green flash. Let's look at some real pictures though. There's an example of a real green flash. You see that little bit of light. Now, a lot of times, most of the pictures that I've seen has been of relatively clear, like at an ocean or someplace like that, where you can get that good far off picture of the sun as it sets. Here's another one. If you look to where the arrow is pointing, you see that little green flash right at the top there. So again, it happens just for an instant. Now we're going to talk some more about refraction, but this is going to be for a different type. It's called mirages. And I know everybody has seen this first type of mirage that I'm going to talk about. It's called an inferior mirage. In this case, the air close to the ground is much warmer than the air above it. And so that causes the light to be refracted so that it looks like the sky, that blue sky, is down on the ground. You can see that especially in the summertime when you have these hot pavements. Again, this was one of those things I can remember driving down the road with my parents when I was probably 4 or 5 years old, and I kept asking why there was water on the road. And I think my parents said, well, just keep looking, it'll evaporate as you get closer. And so yeah, I believe that that's what that was for several years. But here's an example of what it looks like. Again, it looks like you have water on the road, or it looks like the sky is on the road, but that's just because from that really hot surface refracting light. And in this instance, you can see it looks like we have a double sun. Now, the type of mirage probably most people have not seen is called the superior image. This is caused when the air close to the ground is really, really cold. And so what that does is it reflects the light so that whatever's on the ground looks like it's upside down and actually hovering above the ground. And this is probably where, if you've heard of people talk about ghost ships during sailing times, that's probably where those images came from. It was from a superior image. And sometimes this is called looming. But here's an example of what that looks like. You can see those icebergs turned upside down and higher than they actually are. And there's an example of where probably ghost ships got their start from. Now let's talk a little bit about halos. All halos come from ice particles. As the light goes through that, it again is refracted. Now there's different types of ice particles out there that can cause different types of halos. We have the disc type ice crystals, we have the columnar type ice crystals. Again, this is probably something that most people have seen over the course of time. There's one that's kind of a U-shaped halo way above the sun. That's called a circumzenal arc. Then there is one that's kind of a flattened out U called the upper tangent arc. And typically that is right at the top of what's called a 22-degree halo. If you see a halo around a sun, that's called a 22-degree halo, and you'll probably see in some cases that upper tangent arc sitting right at the top of that. Right off to the sides, you've got something called a parhelic circle, but the brightest parts of those are called parhelia, or a more common term that we use is sundogs. And then down at the bottom of that halo, you'll see an upside down U that's called a lower tangent arc. You can see these halos just about anywhere. What it takes is just a really thin layer of cirrus clouds. Those light, fluffy clouds that are out there, sometimes they can form a layer of clouds. They're called cumuliform or stratus clouds, or cirrostratus clouds. And as the light comes through those ice crystals, it creates that 22-degree halo. And again, what's happening is the light is coming through that ice crystal and then getting refracted. It gets refracted 22 degrees, so then that's what creates that halo. Here's an example of an upper tangent arc. Now sometimes you can see these really brightly, sometimes you can barely see them at all in some cases. Probably the one that everybody has seen quite a few of are sundogs. Now there's actually a little bit of weather folklore that goes along with these, and I don't know if anybody has heard of these, but I heard this a lot growing up. I grew up on a farm, and lots of different folk tales about the weather, but this one actually has a little bit of truth to it. If you see a sundog to the south of the sun, it may mean warmer weather is approaching. If you see one to the north of the sun, colder weather may be approaching. And that comes into play if you only see one on one side or one on the other. The part where that actually could come into play is if you see it to the south, that could mean that there's a warm front approaching. That's what's creating those cirrus clouds. And so you may get some warmer weather. Not 100% sure, but it can happen. And on the northern side, it may be a cold front that's approaching. So there's a little bit of truth to that little bit of weather folklore. Again, sometimes you may not see it just as a bright light. If the cirrus clouds are a little bit thicker, you may have a little bit of different color to it. And we see more of these typically in the fall, winter, and spring. We don't see as many of these types of phenomena during the summer because our atmosphere is warmer. We don't have as much of that cirrus cloud formation taking place, those ice crystals, and so that's why we don't see that as much in the summertime as we do during other parts of the year. And here's an example of a sun pillar. Looks like a beam of light just shooting out from the sun. Again, it's being caused by those ice crystals from those cirrus clouds. And if you've got haze at nighttime, got a little bit of fog, the same type of thing can happen at night just from lights on the ground. These are called light pillars. Almost looks like an alien attack, doesn't it? Now here's another one that everybody likes to talk about, rainbows. And incredibly beautiful sight to see out there. But if you look at a rainbow, when we think of it just as being that small ring of colors, actually that rainbow is a disk of light. And that rainbow portion is just a part of it. Depending on the size of the raindrops that's being bounced back to your eye from, the larger the raindrops, the less blue that you're going to see with it. So if you look out and you see a rainbow and you really can't see much blue, you also know that the raindrops that's creating that rainbow are fairly large. Sometimes you can see two rainbows, and that secondary rainbow is going to be about 10 degrees farther out, and it's going to be about twice as wide as the original rainbow. And if you look closely, you see that the colors are reversed. Again, all these different wavelengths as it goes through that raindrop and then bounces back out, comes out at a different angle. And so the ones that are changed through larger angles make the sky brighter, so that's what creates that bright disk. So here's an example. You look at the inside, or I guess to the right of that primary rainbow, you see that brightness associated with that. You see the secondary rainbow, it's harder to see, but if you look really close, you can see that the blue is on the left-hand portion of that rainbow as opposed to the right-hand portion on the primary rainbow. Here's another example, and again, you can barely see that secondary rainbow in there. Here is one that was taken just last night from our colleague Peggy Doty up in northern Illinois. You can see that rainbow coming through the trees. And here's one that I took last night from my house in central Illinois. Not quite as easily seen, but still there. And in some cases, if you can barely see that one showing there, it may not even look like there's any rain taking place, but if there's small liquid water droplets that are suspended in the air, you can still get a rainbow. This is something else that probably a lot of people have seen, is a corona. Again, if you've got that thin layer of cirrus cloud sitting out there, as that moonlight comes through there, the diffraction and dispersion of that moonlight actually creates a wider glow of that light around the moon. So here's an example of a moon corona. And hopefully everybody was able to get outside the other night and see the, I think it's called a pink moon, pink supermoon. Here's another picture of a moon corona. And you can see some of the different dispersal of colors in that one as well. Now here's one that the only time you're going to see this one, and this would be really pretty to see, is typically if you have a large mountain range to the east. This is something called alpenglow. And what happens is it's essentially that reddish light from the western part of the sky actually reflects off of clouds down to the ground, or off of mountains. Here's an example of that. Really pretty to see. So again, this would be opposite from the sun. It would be in the eastern part of your viewing area. This is one that some of you may have seen before if you've flown on a commercial jet and like to fly in the window seat, and you look out the window and you look down and you may see what looks like the shadow of the jetliner, and then you see this bright glow around it. That's actually called a glory. And it's just caused by backscattering of that sunlight from the water that's in those clouds. And here's what this looks like. Again, it just follows right along with you as you fly along. Here's another one. Looks a little more ominous, but it's just a part of what nature does. Now here is one that you may not have heard of before, but you may have seen. It's called heiligenschein. When you go out in the morning, when there's dew on the grass, and especially if you're looking off away from the sun, you got your back towards the sun, what you may see from the dew on that grass is your shadow, but then you have this bright area of light around your head. And so it almost looks like you have a halo around your head. Here's what that looks like. So you can see that shadow, you can see that bright spot right where your head is at. Here's another example of it. So if any of you get up early in the morning and want to check that out, take a picture of it, feel free. Here's one more that looks a little bit more ominous, but it's kind of along the same lines. This is called Brockenspector. This is where you have an elongated casting of your shadow. Again, the head area will be kind of illuminated. It almost looks like you got these halo-like rings of colored light. But you see this a lot of times if you have, say, a foggy background, but the sun can still come through a little bit of that. Here's what that looks like. Again, looks very ominous, and that's probably where the name come from, Brockenspector. That one you don't see quite as much illumination of light around the head, but look at this one. That one looks really interesting. And you can see with this one, it's got a little bit more haze associated with it as well. So there's lots of things out there. Lots of really cool things out there, and we could talk more and more about a lot of these different things. But yeah, let's go ahead and go through some questions.
Judith asked, does high water moisture in the air re-radiate heat to the surface?
The high level moisture does to a much lesser extent. That's one of the reasons why, for example, if you have low level clouds at night, you have typically a warmer evening than you would if it was a clear sky, because those low level clouds, essentially what it does is it shuts down what's called the atmospheric window. There are some wavelengths of light, of energy from the earth that's escaping out into space that more or less have a direct shot straight back out. But when you have a low cloud cover, especially at nighttime, as the earth is giving off that heat that it got from the daytime, those clouds slow down that release of heat. And so that's why you have warmer evenings when you have low cloud cover, is because of that. The really high cloud cover doesn't do that nearly as much. Good question.
Sharon asked you to talk a little bit about the northern lights.
Oh, okay. Yeah, that is really neat. That is caused by the Earth's magnetic field. There are these really high energy uh, solar particles. And one of the neat things about our atmosphere and the fact that we do have a magnetic field is it protects us from a lot of that nastier solar energy and those solar particles that are out there. But essentially what happens is those higher energy solar particles react with some gases, and even that high up, we don't really think of the atmosphere being that high up, but there's still a few scattered areas of nitrogen and oxygen that's up at these higher elevations. These solar particles interact with that, and essentially they ionize those gases. And so when it does that, it creates those greenish, different wavy looking types of light, and they more or less kind of get funneled in close to where the northern magnetic pole is and where the southern magnetic pole is. And so that's why you only see it in those polar areas, because the north magnetic pole and the south magnetic pole are not exactly where the north pole and the south pole are, but they're relatively close. So that's why you have to go into those areas to see that, because that's where that energy is getting funneled. Good questions. Keep them coming.
So Mark was asking about the different kinds of twilight. So the civil, nautical, and the astronomical twilight, do those apply to the morning as well? It tends to look
Absolutely
grayer before the dawn.
Yeah, they work exactly the same way. And if you're driving and say you start out at nighttime and you're kind of driving along, and then all of a sudden you just kind of can barely see some light, that would be the beginning of that astronomical twilight. But yeah, it's still going through the same thing, because that sunrise is still going through those phases where it's 12 to 18 degrees below the horizon, 6 to 12 degrees below the horizon, and then 6 to 0 degrees below the horizon. So yeah, it's still doing the very same thing.
Nancy had commented that perhaps this is not pertinent enough to the discussion, but can Dwayne talk about how crops create their own weather, i.e. corn?
Oh, yeah. Well, some of you may have heard of something called the corn sweats. This is when corn, especially when it's getting to tossling stage, when it's growing really, really fast, it transpires or pumps out huge amounts of moisture. Typically, when corn is at that stage, it may pull up and use almost a quarter of an inch of water a day. And so it's funneling us all through the plant, and then a lot of it gets transpired up into the atmosphere. So yeah, it can actually create much higher humidity in those areas where you've got lots of corn being planted. And if it's all pretty much growing at the same stage, yes, it will actually increase humidity in those areas because of that.
That's so cool. I didn't know that. Laura Dirks asked, why does the sky in certain areas of the county feel like a deeper blue, or is it just because those areas are where I go into vacation mode, i.e. Albuquerque, New Mexico, and the Grand Canyon?
Oh, so she's asking if it's bluer, why the sky is bluer like in those areas?
Yeah, why does it feel like a deeper blue, I'm assuming, or is it just her saying that, I'm in
Well,
vacation mode, so I
the
have a
reason
better
for that,
outlook.
yeah, yeah. Typically, when you have drier air, you don't have as much of that, kind of like what I was talking about when you see the whiter color to the sky as you get closer to the ground. That's because of the humidity and because of the water droplets. Out in Arizona, big sky country, Wyoming, Montana, those areas have much lower humidity. And so that's why you have that deeper, there it actually is a deeper blue in those areas. I mean, I would think, especially you get into some areas like Nevada, there's one place called Elko, Nevada, that has incredibly low humidity. Uh, the sky might even look almost that indigo color, really deep blue. So yeah, the drier the atmosphere is, typically the bluer the sky is going to be.
Excellent. So it's not just Laura being vacation mode, although I wish we all were in vacation mode right now.
Yeah. Now, if you went to Cancun or someplace like that, I don't think you would see that deeper blue to the sky there. It's going to have to be in an area that's relatively dry in terms of humidity.
Excellent. All right. So Arnie asked, what is the relationship between light waves or wavelength and photons?
Well, that's a really good question. Actually, the light travels as a wave, but it also travels in the form of particles of light called photons. So those photons are traveling through the space, through the atmosphere, in relatively straight lines with that wavy travel to it. But what's traveling through there are those photons. So that's getting into another. That's getting into more of a physical science or physics topic. But yeah, I mean, their photons are out there, and anybody that's a Star Trek fan has seen those photon torpedoes being shot off by the USS Enterprise. Yep, there actually are photons, particles of energy that are coming through on those wavelengths.
All right. Alan had stated that in the 1990s, I saw the Northern Lights in Evanston, Illinois, one fall evening when I was walking at Northwestern University Lakeville. How was that possible? I wasn't hallucinating.
That's a really good question, and I think there was something close to that happened this last winter. In some cases, when the sun shoots out a huge amount of solar particles, more or less like a solar storm, it's just inundates the magnetic field. And so when you get those types of situations, you can see the northern lights at a lower latitude. The side effect of that is if that solar storm is strong enough, we have to really be careful in terms of our internet and our satellites and all those things, because that can be very damaging to those types of things also. But that's one of the main reasons why, is because it's a situation where the sun has shot off just a huge amount of solar particles called the solar wind.
All right. Another user had asked, is the harvest moon that is huge a refraction that enlarges?
Well, it's kind of like the super moon we had and are having. The moon's distance from the Earth varies a little bit, and it happens such that when, depending on how all that works out, and you hear them talk about supermoons, it's larger typically because at that point during the year, it's closer to the Earth, and so we simply see it as a larger object. These are really good questions. You guys are doing
Yeah.
fantastic. If you were in my weather class, I'd give you all 10 points.
Kristen asked, I live near the Wisconsin border along the lake and see Chicago skyscrapers when walking along the lake. That's a mirage, isn't it? I live 45 miles away from Chicago.
Probably. That's a really good question. Typically, for us to look off onto the horizon, even if we have a really flat landscape, about the farthest we can see to the horizon is about 7 to 10 miles. Now, those tallest skyscrapers, maybe But yeah, it could very well be a refraction that's taking place.
Laura had asked, could you explain the greenhouse gas point you mentioned at the beginning of the talk? I'm not sure how the trapping idea has become so dominant if it is a speed issue.
Yeah, that's and I think it's one of the things that people just use it as a common term. But what happens is this heat it comes, that visible light comes through the atmosphere. Most of it doesn't heat the atmosphere directly. It's got to heat the Earth's surface or hit the Earth's surface. The Earth's surface then gives that energy up to send back out into space. A small portion of it just escapes directly back out into space. But what happens to a good portion of it is, as it's trying to escape, it gets absorbed by a greenhouse gas. When a greenhouse gas absorbs it, it releases it back off, but kind of think of it as a little microscopic sun. It's giving that energy, that heat off in all directions. So a small portion of it does go on up, and probably gets absorbed by another greenhouse gas, but a large portion of that heat gets moved sideways or back down to the Earth's surface. And so essentially what it's doing is it's slowing down how fast that heat can escape back out. So, it kind of goes through this back and forth motion from the Earth to these greenhouse gases, with a little bit escaping every single time it goes through that. So eventually that one unit of heat does escape, but it's not like it can jump directly back out into space. It takes some time to do that. And the other thing to know is that there is a natural greenhouse effect that's been around for millions of years. If we had no greenhouse effect whatsoever, Earth's average temperature would be about 5 degrees Fahrenheit instead of what it actually is, which is about 59. And that's because we've always had a certain amount of greenhouse gases in the atmosphere, things like carbon dioxide, methane, those kind of things. But when we talk about, and what a lot of folks don't stipulate between the two, there is an enhanced greenhouse effect that's going on. And it's just cause and effect. It's simply that. Because if you add more greenhouse gases into the atmosphere, which has been done in the last 150 years, you're going to have more opportunity for that absorption of heat, and then it's going to take longer for that heat to escape. And that's what the enhanced greenhouse effect is. And so it simply takes a little bit longer for that heat to escape. And so that's when you got into the terms of global warming. And of course, then that's kind of been shoved aside with climate change, and now it's climate resiliency. So, if people were interested, I could do a webinar at some point on all of these things. The regular greenhouse effect, the enhanced greenhouse effect, how all of that works. So that might be something we do farther down the road. I've really enjoyed talking with you today. I've really enjoyed the questions. Hopefully you've enjoyed the day as well. Thank you again. Have a good day, everyone.